In this lecture, we will see the schematic diagram of a CMOS latch, and then we'll draw the twisted schematic and then the layout. So this is a CMOS latch. We all know what is a latch and what is a flip-flop. Latch stores 1 bit of data. In this lecture, we will learn about the CMOS D-latch. Okay. There are many methods by which we can model a latch by using NOR gates. So we need to understand what is the function of a latch. The function of a latch can be seen as, suppose it's a SR latch. We have Q and Q bar. If 0 0, then the output is Q. 0 1, then 0. 1 0, then 1. 1 1, then it's invalid. This is the SR latch output for the SR latch using NOR gate. Which is something like this. This is S, this is R, this is Q, and this is Q bar. Okay. So now if I want to construct a D latch, then if I want to construct a D latch, then this is the input D. Okay. This is D. And the inverted of D is given over here. Here we have the clock. This is clock. Now this is the input S for the next NOR gates, and this is the output from these AND gates. This is a NOR gate. This is a NOR gate. Okay. So this part is the this is Q and this is Q bar. So now we'll see the schematic diagram of a D-latch, CMOS D-latch using the transmission gates. Of a CMOS latch, if we use the transmission gates in a CMOS latch, then the schematic will be one transmission gate over here, this is PMOS and MOS, this is the input D, this is the control input C, and this is C bar, the complement. Then we will place two inverters over here. Okay, so this is VDD and this is ground. So this will just act like a buffer. So we'll connect another inverter. PMOS and NMOS. This is also VDD. This is ground. So now this is the output Q. Now when C is equal to 1, then this is activated, this transmission gate. So we'll place a transmission gate so that when the control input C is equal to, when C is equal to 0, then this transmission gate will work. Okay, so this is C bar and this is C. Okay, we'll use a inverter for connecting C and C bar. So this is VDD, this is ground, this is C, this is C bar. So C bar is connected over here and over here. Similarly, we can connect this C. This is C, this is C. Now, if you see the operation of this, the schematic diagram, then let's first discuss that what is the function of a standard D latch? A standard D latch, which is a level control flip flop, can be built from 4 2 input NAND gates. So total 16 transistors will be used if we try to use 2 input 4 NAND gates. So if we design using this transmission gate, then this is reduced to 8 transistors. Okay, which is done by using 2 transmission gates and 2 inverters. So now the transmission gate which is present over here is controlled by the input C. This is the control input C. C is the controlled input. There is a feedback transmission gate. This is the feedback transmission gate, which is controlled by the negation of C, that is C bar. The function of the transmission gate is conducting, and the data input value is connected to the first inverter input, which generates D. Here, if we get D, then here we'll get D bar, then again here we'll get D. So this just acts like a buffer which buffers D to the output Q. So when C is equal to 1, we know that when input is 1, then PMOS turns off and the NMOS turns on. When input is 0, then the PMOS turns on and the NMOS turns off. So when the control input is 1, then this NMOS will turn on. Suppose this is P1, this is N1, this is P2, N2, this is P3, N3, P4 and N4. This is the inverter. So when C is 1, then here C bar will be equal to 0. Then this transmission gate will be activated, and over here C bar becomes 0 and here C is equal to 1. So this transmission gate 2 will be inactive, and the transmission gate 1 gets activated. So this input D will be seen in the output. When this passes over the two inverters, we'll get output as D. So the value of Q becomes D. So when C becomes 0, then C bar will be equal to 1. So this PMOS will turn off since the input is 1, and this NMOS will also turn off since input is 0. Here the input is 0, the input is 1. So this transmission gate will be activated. And this will get inactivated. So now what will be seen in the output? Because this input is not passed to this transmission gate, so whatever the earlier value of Q, the previous output will be seen in the next output. So this is the operation of the D latch. Now let's see the gate level diagram of a latch. This is a typical gate level latch schematic. Now we have two transmission gates as discussed earlier. Okay. This is transmission gate 1. The input is D. This is X. This is C. And this is C bar, the complementary. Now we have another transmission gate. Here C and C bar is given in this manner. Okay. So as discussed, this will turn on when C is equal to 1. This will turn on when C is equal to 0. So we'll have a buffer over here. That is connected after this first transmission gate. This is inverter 1, inverter 2, this is the output Q. Earlier we had drawn a rough schematic diagram. This is the gate level diagram of a CMOS latch, where this is the transmission gate 1. This is the transmission gate 2. This is inverter 1 and this is inverter 2. This whole acts as a buffer. So whatever you'll apply here, you'll get the output over here. Why this buffer is needed? What is the significance of buffer? It helps. Actually, here the value is not stored, but it helps to store the previous value of Q, which will be used later on. Q, that is D. Actually, it stores the value of D in Q. So this value is needed when your C becomes, when C is equal to 0, then this is helpful, because when C is equal to 0, then transmission gate 1 is inactive and transmission gate 2 is active. So this input D does not pass to the output. So D does not pass to the output. So that's the reason why you need this buffer, so that when C is equal to 1, when at first C will be 1, then this value of D will be obtained at the output, and here this value will be stored. So now, so this was the gate level diagram of a CMOS latch. Now let's see the schematic diagram by using the PMOS and NMOS. This is the normal schematic diagram. Diagram of a CMOS D-latch. Okay, so first we'll draw the two transmission gates. As we know that there were total two transmission gates and two inverters. Suppose this is transmission gate 1, okay, this is C and this is C bar, input D, this is the output. The output was X, which was connected to the second transmission gate. Here it was C bar and here C. The output was Q. This was X. Okay. Now the X was, that means over here there was another inverter and another inverter. So that we can draw over here also. So this is the gate. From the gate, input was given. This is X. Here from this position, From this position up to this, we had two inverter present over here that we are drawing here. This is X and X. This was connected to VDD. Okay, and here this was connected to ground. These are the drain terminals. From here again another inverter was placed. So let's say the output was Y over here. So the input of the next inverter would be Y. So this is connected to VDD. This is connected to ground. This is Y. This is Y. And this is the final output, that is Q. So a section that is present between these two, let's say the section 1, it's shown over here. This is section 1. Okay, so if you want to represent, or if you want to draw the transmission gates in a different way, or you can see over here that we put contact like this. We could have done it directly, that is we could have joined it directly without placing this contact. So now let's see another form of the schematic diagram, that is if we join the terminals, then the schematic diagram would have, this is the continuation of normal schematic. Normal schematic diagram. So select this. This is the input D. This is the output. Okay, this is what had to be changed over here. Instead of placing, or instead of attaching again, we could just draw it directly over here. Directly just will connect. Okay, so this point is the X point. This is PMOS 1, NMOS 1, PMOS 2, this is NMOS 2, this is source, drain, and this is again source and drain. Now over here we have two inverters. This is X. Here this is C bar, C. This is C. This is C bar. And this is VDD. So this is X and X. This is ground. And here this X is connected to this X, and this X is connected to this X. Okay. Now here the output Y is, this is the output Y, which is connected to another inverter. This is Y, which is not connected to VDD. This is the source connected to VDD. This is again Y, and this is connected to ground. So from ground, this and this Y will be connected to this and this. This is the final output Q. So from here the output is Q. Okay. So this is P3, N3, P4, N4. So this was the normal schematic. So now we'll obtain the twisted schematic. Next we have to form the twisted schematic so as to draw the layout. Now let's see the twisted schematic diagram. Twisted schematic diagram. We'll just undo this. See the twisted schematic diagram of a CMOS latch. So since there were 4 PMOS and 4 NMOS, that is 2 transmission gates, then each with 1 PMOS and MOS. So we'll have 2 PMOS, 2 NMOS from the transmission gates, and from the inverters we'll have 2 PMOS and 2 NMOS. So total 4 PMOS and 4 NMOS. So at first draw the PMOS. This is PMOS 1. This is PMOS 2. This is PMOS 3. This is PMOS 4. Similarly, we'll have NMOS 1, NMOS 2, NMOS 3. This is NMOS 4. So now P1, P2, P3, P4, N1, N2, N3 and N4. Now this is the source drain, okay. So in a transmission gate we know the sources of PMOS and NMOS are connected and the drains of PMOS and NMOS are connected and the gates are interlinked. That is, the gate of PMOS 1 is connected to the gate of NMOS 2. That is, PMOS of transmission gate 1 is connected to the NMOS of transmission gate 2. So this is a transmission gate 1. So first you will connect these sources, then the drains. Similarly, the sources over here, drain here. Okay. These two are the inverters that we'll see later on. So this is the gate. The gate will be connected like this. And from here, for showing the schematic, we could have done it directly, but from here directly we can have an idea to draw the layout. So we have to draw the schematic in a way we are drawing the layout. Okay, now these are the two inverters. This is the source, this is the drain, source, drain, source, drain and source, drain. The source of the first inverter is connected to VDD, or we can do one thing, we can change this by bringing drain here, source here, or we can change the source by here, so that way we can have a common point. So we just undo the names. Now this is drain, source, drain, source, source, drain, source and drain. So these two are the inverters. The gate of PMOS and NMOS and an inverter are connected. Similarly over here. Now the sources of PMOS for both the inverters, it's connected to VDD, and the sources of the NMOS are connected to ground. So we can just connect here directly, then connect to VDD. From here connect to ground. From here the drains are connected because the output of the inverter is obtained from the drain. Similarly over here. Okay, so this is the input, Suppose this is input Y and this is input X, then the output obtained will be this is the inverter form. Okay, so we know that from the schematic, that is, this was X, this was the output of X, this was Y, the output of X was Y. So here this is the output of X that is connected to Y. So this Y is connected to X. Okay, connected to here. Okay, so now this is the X is connected to the input. So here this is also connected, we know. So to this point X is connected. Okay, now X is given, the output is obtained from here, these two junctions. This is the output Q. So if you want to modify the schematic in a more proper way, that is, if you want to draw the layout with single N-well and single P diffusion, because in this way you have to use two P diffusion separately, and this is the third P diffusion. Similarly with the N diffusion layer. So from layout point of view, you can change the schematic. Then it would be like this. Okay, this is P1, P2, P3, P4, N1, N2, N3, and N4. So now this is the source drain. So these sources of the first, this is the transmission gate 1, transmission gate 2, inverter 1, inverter 2. This schematic is for single N-well, P diffusion and N diffusion in magic layout. This schematic is drawn by keeping the layout in mind. So this is connected to give the input D. Okay, now this is the transmission gate, The gates are connected in this way. This is the inverter. So the gates of the inverter are connected. Okay. So now this is the output of the two transmission gates. Okay. So connect these two. This is Q. Okay. This point is Q. That is, this is the output Q. Now this is the drain, source drain. So here VDD, and over here ground drain. Okay. So now this is Y and this was X. So the X, this is X. So if you remember from the schematic, X was connected to this. Similarly here, X was connected over here, and Y was connected. Y is actually the output of X. So Y is actually the output of X, and the output of Y is Q. The output of the inverter 2 is Q. Okay. So now let's see. Now we will see the layout of the CMOS latch. Now let's see the layout of a CMOS latch. That is drawn from the twisted schematic diagram. So at first, from the previous schematic, that is the schematic where we had taken, which was drawn from the point of view to use a single N-well and a single P diffusion layer. So with reference to it, we'll take one N-well. We'll take a single N-well. Single N-well, and a single P diffusion layer. Okay, so this is a P diffusion layer. So this was the PMOS. So next we have to construct the NMOS. Okay, so we'll take a So first you have to draw the gates so that you can distinguish which part is the transmission gate part and which is the inverter part. So this is gate 1, gate 2. Okay, let's take the inverter gates first. Suppose this is inverter gate 1 and this is inverter gate 2, transmission gate 1, transmission gate 2. Similarly, mention the dots here just for your convenience. Okay, will not draw like this in your magic, but just for your convenience. So similarly over here. Now over here, this is the poly layer. So now this is the drain. This is a source connected that gives you the input T. Okay, so this was the input D. This is D, and this point was connected to here. This is Y, this is X. So before that, we'll connect this later on. This is connected. Okay, this is the output Q. This is your C. This is your C bar, and this is your C. Okay, now actually, if you want, we could have done one thing that we'll discuss later on. This is Q, this is Y, the output, or this is the output of Y, and here we'll get the output of X. The output of X inverter, that is X bar, is nothing but Y. So connect from here to here. This is your metal layer, metal 1. and we'll place a poly contact. Here there will be a poly contact over here. Okay, now this was output of, that was x bar or equal to y. Here this is your VDD. This part was connected to VDD. So this is VDD and this was connected to ground. This is nothing but the source part. This is ground. Now this X is connected over here and over here. So can do one thing. You have to connect from this is connected to this. Similarly over here you will connect from here. So this is a point where X is connected. Okay, we can directly connect over here because this is also connected to X. So you have to place a poly contact. This is your poly contact. So you have to place the substrate contact in the VDD and ground layer. So select the area. This is the N substrate contact. This is the N. Similarly over here, you have to place a P substrate contact. Or PWC contact. This is your NWC contact. In order to make a contact between the P diffusion layer and this, you have to place PWC contact. P diffusion contact. Similarly over here you have to place N diffusion contact. This is your NDC contact. This is the layout of your CMOS latch.